So are there questions from Chapter 8? Homework? Are you guys doing Chapter 8 homework? You got to remind me. Good. You got to remind me. Yeah. Please remind me. I only have a few of you guys online, so I sometimes forget. So don't let me keep that away from you for too long. Just let me know when that happens. Okay. That's a really good excuse you have for not having questions, because I have not given you anything to work with yet. So they have an excuse. So I'm going to assume that means it's going pretty well. Okay. But the nice thing, I want you to realize the nice thing about Chapter 8, and I know this is not the nicest thing it could be, but once you get that idea down, those 5 steps, they never change. It's just sometimes you use z-scores, sometimes you use t-scores, sometimes you use z equals p hat minus p over square root of p q over n, or you use the z-score, that formula that we're used to. But the steps don't change, right? It's what the hell are you talking about? What are you going to use? What's good enough evidence? Did you find evidence? And then sum up what the hell you just did. Those are the 5 steps in technical terms, right? You guys might notice that there are, just to kind of let you know, there are some sections at the end of Chapter 7 and Chapter 8 that I put off till the end of the semester because they deal with an entirely different distribution. So I wanted to focus on all the stuff that uses the normal distribution, and then towards the end of the semester we'll deal with the stuff that uses this other distribution, the chi-square distribution. Yeah. Oh yeah.
How do you write that?
You can make up any word you want to right now, Jeff. I pretty much don't know what the hell you're talking about anyway. But that's in the future. We don't know what the hell it's supposed to be yet, so that's going to be coming up later. So what I want to do right now is to give you a little bit of motivation for why the hell Chapter 9 exists. So, Chapter 7, I know we just did the quiz on it, and it sounds like we didn't like it too much, but normally people like Chapter 7 because it's formulas you just got to plug and chug. The beautiful thing is, Z or T freaks people out, but the formula tells you when to use which one. You just have to actually figure out from the problem which situation you're in, right? So, Chapter 7 started with something that's not very realistic, but still sometimes true. And I want you guys to, I want to get this idea really far across. So, now that we're in Chapter 8, I can talk about this like this. If you wanted to test a claim about there's a group of people in a certain state that have very tall men, right? All the men that are born in this little neighborhood are tall. So you're going to compare their heights to everybody else's heights to test a claim. Are they really taller than average or not? So you can do a hypothesis test for that. Are you guys kind of with me? You know the standard deviation of the population because they are a part of the population. All American men, the heights are standard deviation of 2 point whatever the hell. I can't remember what it was now. You guys kind of with me? So that's why sometimes it's okay. It's not unrealistic that we will sometimes know the population standard deviation even though we're working with a sample. It's because our sample comes from a population that we already know a lot about. We're just testing a claim. Are they unusually tall? Is this group unusually skinny? Is this group having unusually many babies or whatever? You guys kind of with me? A little bit? A little time bit? But it's still kind of unrealistic for other things to expect that I would know the population standard deviation because I often don't know crap about the population. That's the whole point. So if I wanted to do something like compare the grades of the men and the women in this class and see if they were statistically different, statistically significantly different. Are you guys kind of with me so far? So they could be different, but I don't know if they're statistically significantly different until I do a hypothesis test. You guys kind of, I want to see how far apart are they relatively. If they're not that far apart relatively, okay, I'm cool with that. That's not significant difference, right? If they are, it's like, oh, one is smarter than the other one, or one studies more, or whatever the hell. You guys kind of with me? So the problem with that, with what we know so far, with Chapter 8, is Chapter 8 is always comparing to a known mean. or percentage based on which one you're doing. So, for example, let me see. So we have tests. I can use Z star. You got this little dude, right? So always comparing a sample mean to a known mean or somebody's guess or whatever, but this is what we assume to be the real mean. And we're seeing how far away is our sample to test if that makes sense that that's the real mean. All right, guys, with me so far? So if you say, I think the average age of Grossman is 30, and I go took a sample and I find my sample is 5 standard deviations away from your guess, I can pretty much say you are wrong. It's a very small chance that I'm wrong. You guys kind of with me? I mean, this is the whole idea behind chapter 8. In the situation I was just talking about, if I wanted to compare the men's grades versus the women's grades, that would be 2 samples. You with me? That wouldn't be one sample versus some big population or some known number, you guys. So I need a different formula. What sucks about this formula is there's only one place for sample information. I want to compare 2 sample means to each other. I want to see if they're far enough apart. Okay, maybe. So let's do this. Let me ask you. Let's keep going with the men and the women's grades. So if I think the men's grades, men's average grade. And let's make this a little bit bigger than just this class. We'll say, in my stats class, in all the stats classes I've ever taught, I think the men's average grade in all the stats classes I've ever taught is the same as the women's grades, average grade, mean grade, whatever the hell. How are we doing so far? So that should sound something like a statement you would see in a Chapter 8 problem, right? That's a claim that I'm making about something, but the difference here is how many populations are really involved. 2, and those populations are men and women. It's crazy, right? The grades of those people. Right? So I got the population of men and their grades, and the population of women and their grades. Yes, sir?
This is dealing with population, so we use these.
You're all, now be careful. I'm always dealing with populations because that's where I get my samples from. Whether I'm going to use a Z or a T score depends on which standard deviation that I know.
Yeah.
You kind of with me? All right, cool. How you doing so far? So, chapter 9, there's 3 sections in there. One of them is going to be like this one. It's going to deal with means. Another one's going to deal with percentages. And then the last one is going to look at means again in a different way. I'm trying to remember which order they come in. Okay. But the main idea I want to get right now is the steps are all the same. So the first step is the same. It's right, here's where things get interesting. What did you guys just tell me? How many populations am I dealing with? 2. So let's define those 2 populations. We'll call men population 1 and women population 2, going alphabetically. Right? I'm not saying anybody's better than anybody else. So we'll say men have a mean of mu1, and women have a mean of mu2. Now I want you to realize what's going to happen is I'm trying to develop a z-score formula that has room in it for 2 samples. The minute I start doing that, I can't just have x bar. I have to have x bar 1 and x bar 2. Does that make sense? Otherwise, x bar minus x bar is 0. Everything's 0. Screw it. That's easy. Can't do that shit. All right. So I'm going to have a lot of little subscripts on a lot of things. So if I call them this, and this is the first step you have to take, you have to know what the hell does 1 reference and what the hell does 2 reference, so you don't put something in the wrong place, or else your formula is going to come out negative or something. So in mathish, what is the claim that's being made? How would I write it in math? And actually, which one is it going to be? This one you should, which is it going to be the whole or the high? The whole, because the claim has an equals in it.
Equals, yeah.
So I know it has an equals in it.
Mu equals mu1 equals mu2.
Yeah. So if I would have said I think that men's average is more than women's average, I would have said mu1 is bigger than mu2, right? So the first real little difference is in chapter 8, I would say mu greater than 7, or mu equals 122. You with me? Here I'm comparing two means. That's the only difference. So I say this mean equals that mean, or this mean is bigger than that mean, or whatever. So like you guys said, this is definitely going to be the HO. And the H1, incredibly enough, is going to be
not equal. Not equal.
That's still
Negated.
I like it. How are you doing so far? Not too bad, right? Okay. So, then I'd have to do step 2 is the same as always, really. And we'll do, step 2 is still Z or T. We're not going to do this whole problem out. I haven't given you any information here yet, have I? I just want to focus right now on the differences, and then we're going to try to do an entire problem together. But I want to show you what's really different. The formula is going to look a little bit bigger. It's not really going to be different, believe it or not. So this is still the same, and I still determine this the same way. But now instead of sigma or S, I'm going to have sigma 1, sigma 2, or S1, S2. You with me? A little bit? Because I'm going to have two different populations. Again, I like it. I like it. So it's still determined the exact same way. The T thing we'll get in a little bit because the degrees of freedom gets a little weird because how many sample sizes will I have? Two. So how the hell do I figure out degrees of freedom? So we'll talk about that a little bit.
Do we do 2 degrees of freedom?
We'll talk about it. Don't worry. The third step is really the same. It's going to be the rejection region. Right? Tell me what's far enough away. So it depends on what sets up your rejection region. Somebody tell me, what does it depend on? The confidence is not really the right thing to come up into with this.
Degrees of freedom? Or no?
If it's a t-score, it depends on degrees of freedom. In general, it might depend on the sample size, but it definitely depends on alpha. Right? And somebody tell me, what is alpha? What's the name of alpha? What is that?
The 2 points. The 1 or 2 points.
Have I used this phrase yet? Level of significance?
Yeah.
Because you make alpha smaller and you pass the test, it's more significant. You've passed a harder test. So, I mean, it's more proof. So that's why it's called level of significance. Right, so it depends on that. It depends on if it's 1 or 2 tail. Right, it depends on if it's Z or T. So then it would depend on degrees of freedom. So all those things got to come together, and that's how you figure out what score, what's the critical score, like the book says, for that rejection region. I don't really use that word, but yeah.
Like it has to be with like inside the rejection region, like.
You figure out where that rejection region is. That's step 3. Yeah. Step 4 then is, did you get in there or not?
Oh yeah.
Cool. So I desperately want you to see the steps are the same, thank God. Right? Because this is freaky enough. So the steps are the same all the way throughout. It's just the little parts in them. This is a little bit different. This is going to have a little bit of difference because there's 2 ends. And now 4 is the one that's got the most difference. So let's work on that by itself here. Let me give it its own area to look at. So the Z-star formula. So the old one, again, was like this. Now, obviously, I'm talking about means. We're going to have to develop a new one for percentages also. So this is just seeing how far apart a mean is, what's the distance between a mean of a sample and the supposed mean of the population. Just want to see how different those are, right? If they're very different, then it's evidence that it's really, this one is wrong. So what I'm going to do now instead is I'm going to say, all right, I want to see how different are my samples from each other.
Minus.
And then compare that to how different should my sample means be. So I took this guy, effectively what I did was I took this guy and split it into two. I took this guy and split it into two. So I want to see how different, this is going to sound weird. Thankfully we're not going to deal with this for very long. But I want to have the difference between these two differences. Right? So if I think one mean is supposed to be 3 more than the other one, and I get my sample mean is 20 more than the other one, well, that's a big difference between what those differences are supposed to be. You guys still kind of with me? Some of you guys are like, no. Shit. So the whole idea here is, for example, ours, what's the difference supposed to be between the means? Nothing. In fact, the HO for us, in general, this actually is not necessarily true. The HO will always have an equal sign in it.
So 0.
Right? You could have some claims that are like what I just said. I think that these are exactly 3 more than this. That's where things get a little weird. We're not going to go there too much because this is weird enough already. Our HO is pretty much always got to have an equal sign in it. So what's the beautiful thing that's always going to happen to this piece? Because we're assuming, we always say, assuming you're right, assuming this thing is right,
0.
Let's go do some stuff. So if I assume this is right, this piece is
Nothing.
0. Now if I said I think that this is 3 more than the other one, then this piece would be 3, because they're supposed to be 3 apart, right? Taking that next step wouldn't be that difficult. But the beautiful thing is, just to get into this, let's just forget about the whole part of the equation. That's 0. Okay, maybe. Yes, sir.
So we don't know the X bar 1, the X bar 2. They're not.
Yeah, they'll have to either be given to me, or I have to get lists of data and I can calculate them using the calculator.
Do we do the same thing for the standard deviation, like subtract 1 from the other?
All right, here we go. Now, the standard deviation is a little bit freakier, as you probably should know it should be, right? And I can't remember now, because I am, just like chapter 7 and 8, I am doing this in a little different order, I think. And I think this is 9.3. Yeah, 9.2 is the proportions thing. I really wish I understood why they do that. But I just will accept that I will never know. Now, somebody help me out. This piece here, what's the real formula for that? For the new standard deviation?
Sigma over n square root.
Yeah, the old one divided by square root of n.
Yeah.
All right, now, just go with me. And you know, some of you guys just agree with what he says, so he'll get to the end of this. But couldn't I say that's the same thing as the square root of sigma squared over n? Think about it for a second. What's square root of sigma squared?
Sigma.
Sigma, right? You know it's not plus or minus because sigma's got to be positive, right? So these are the exact same. And you're like, ooh.
Yeah.
What the hell's that got to do with it? Because now what I could do on the bottom is, instead of having just a single standard deviation, I now want to have 2 of them. But the way this has to work, and I'm definitely not getting any deeper into the mathematics of why this must be the way it is, I want you to focus on, I've got 1 sample in this one, I've got to have 2 samples in this one for chapter 9. Here's how the math works for this. 1 big ass square root, and you put your sigma 1 squared, your sigma 2 squared, like so. That's the way that variances end up having to work.
Do you have to have the same M?
No, I'm thankful. I knew I was forgetting something.
Yeah.
And that came up earlier this semester, and the answer was fine that it was wrong because you didn't realize it wasn't a big deal. But you definitely don't have the same numbers of people in each one. So if you're doing a drug study, if you give the drug to 637 people, you can give a placebo to 400 people. Who cares? You're looking at the rates, right? You're looking at the percentages. There we go. That will change the degrees of freedom. That'll change your rejection region. But it doesn't have a damn thing. You don't have to have the same sample size. So thank you. All right. So I want you to realize all I did was there's 2 of these now. And there's 2 of these now. That's really all there is to it. And I love the fact that...
And 2 of mu also.
Yeah, and those effectively go away most of the time. Especially for us, all the time they will for us. I love the idea then you can see what's most important if you think that two populations are different. When you take a sample from each, what do you want to look at to kind of prove that? So if I took a sample, if I think the women are higher than the men, if I take a sample of women's grades and a sample of men's grades, what would I look at?
Total.
So if the men's average grade was a 75 and the women's was a 78, what's important about that? The difference. They're 3 apart. And I want to see, is that 3 apart? Is that evidence that the population of men and women in my stats classes is actually different? Are you guys with me? So the top here makes total sense. How far apart are the means from each sample? The further they are apart, the bigger my Z star will be, the more evidence there will be for some actual difference existing. How are we doing so far? Yes?
So that's the sample, like x bar minus...
Definitely. That's the sample mean, right?
Yeah.
So this is the sample mean for, in our case, men. And this is the sample mean for women. Cool? Because we define 1 to be men, 2 to be women. How are we doing? You're loving it. I know, I can tell. Okay. You're all like, I don't understand 8. It's got more shit in it. Sorry. And some of you guys are laughing because you're like, yeah. So let's try a problem out. Let me make up some numbers. I didn't actually run this because it could be controversial, but who knows? So let's make up some numbers. Let's say...
I was very interested in it.
I know. Maybe I will do it. And by the way, this is the way you start to investigate discriminatory practices or racial inequalities. You start to see... Now, when you do this, anybody watch Mythbusters? And I haven't referenced Mythbusters as much as I normally do in a stats class for some reason, but I just love that show. They often get into the idea of accounting for other variables. So just because there might be a group of people that have a lower average than another group of people, maybe there's something common for this group of people that would force them to have a lower average. So it's not the school's fault, it's just the way things are. But if you account for that and you still see a statistical significant difference, then you're like, what the hell are you guys doing? Something's wrong. Somewhere, something's happening that shouldn't be happening. You guys kind of with me? A little tiny bit. So let's say for the men, let's say the X bar, we take a sample of men and we get an X bar of, what did I say earlier, 75, and we know the standard deviation for the men is, what makes sense, Jeff? Like 10.13, and we looked at 198 men. So far, so good. So that some of the early problems actually just set it up exactly like this, and then the later problems are these big-ass paragraphs where you have to pick out everything and make sure you call everything the right thing. 1's here and the 2's there. Right? You don't want to mix them around. So for the women, let's say I get X bar 1 is, yeah, there's 1, 2, 78. Sigma 2 is, let's say 11.75, and N2 is 163. How we doing so far? A little good. Okay. So let's focus on, first off, step 1 we already did. Step 1 you guys have written in your notes, right? So this is going to be kind of a little bit scattered. Step 2, could I use Z or T? What 2 things you have to know? What thing you have to know first to use any damn thing?
If it's population step or if it's
No, first thing you have to know if it's normal.
normal.
And what tells me it's normal enough?
Above 30. Above 30.
Yeah, both these sample sizes are above 30, right? If one of them was below 30, then you'd have some problems, unless somewhere it said it was normal. the population, right? You guys with me?
Standard deviation is known.
Good.
The population-
And the population standard deviation for each
Z.
one is
So
known.
we use Z.
So we can use z-scores. I like it. So we use z-scores, normal enough. Check. Sigma known, 1 and 2. Check. All right. So, as I sometimes do, I might give you alpha on the third step. So if I said alpha is 0.05, how many tail tests is this going to be?
Two.
Yeah, how do you tell? What do you look at to see how many tail tests it's going to be?
Because alpha's
Says like is or something.
So I'll tell you this. Recall HO was this. Get out of there. H1 was this. And you always look at H1 for the rejection, for the tails. 1 or 2 tail test.
two tail two.
So in this case, 2 tail, because not equal to could mean bigger or smaller. So either way it goes, to show that it's not equal to, I don't care who's on top. I don't care. This could go either way. So alpha 0.05. It's a 2 tail test. Can somebody help me out and tell me what that boundary point is on those sides there?
Point 95.
196.
Good, 1.96. And that's the one that goes way back to the empirical rule. Remember that said within 2 standard deviations there's 95%? So we refined it a little bit. It's not exactly 2, it's 1.96. So if Z star is
X bar.
if Z star is what, I'll do what. If Z star is what, I'll do what. Blah, 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 blah.
Oh,
Say it again, Jeff. No.
No, these days is 1.96 and above. Below 1.96.
Yeah, if it's less than 196 is in there, right? Or if it's
Above.
greater than 1.9, positive 196 is in there. It's far enough away then. So if it's far enough away, I'll do what? Reject. The null. I like it. Reject the null, support H1. So obviously, the better you've done and the better you understand Chapter 8, the easier Chapter 9 will be. If you understand Chapter 8 really well, Chapter 9 should be really easy. The only real difference is Step 4. The formula looks different. But I really want you to understand, our data minus the accepted middle divided by the standard deviation, the damn z-score formula never changes. The parts of it look different in different situations. Maybe. And you're like, screw you, Jeff, it changed. All right. I understand. Oh. All right, so now we're to the point where we want to try to use this formula with that information. So let me take this out of here. We're in Step 4. I'm going to let you guys go for it. So here's the let me write the formula again because it's gotten a little bit overrun. You got to be really careful about parentheses here when you put it in your calculator.
What about mu, or is it just?
Remember, in this case, I just erased the hypotheses, but the hypothesis was mu1 equals mu2, so this piece will be 0. In fact, for us, it will always be 0. In the real world, it's not always 0. The easiest thing to forget in this formula are these squares in here. People always forget the square of the standard deviation, and the whole thing goes crazy. So has anybody got a
Negative 2.568.
negative 2.568?
I got a 197.
197.
Controversy, I love it. All right, so let me see real quick. So 5 minus 78 divided by square root. Bless you. Yeah, I got negative 25675.
68.
Yeah, exactly. So I agree with the, if you got 2567 blah blah blah.
You don't square it.
Yes, you do.
Yes.
You got to square root that bottom. So this simple step from chapter 8 to chapter 9 opens the door to everything. And I know you guys are not obviously probably as excited about stats as I am, but what we've just done is we've opened the door to, we don't have a freaking clue about the population, we don't have a clue about anything, but if I just go take a sample of people from Wyoming and a sample of people from Nevada, I can test a claim about differences between people from those states. You see, bam! That's all I got to do is go actually talk to people, get numbers, throw it in there and see if they're different. Right? Oh. The looks in some faces are like, yeah, you obviously get something out of this. All right. So what does that mean for our whole thing here? I forgot what it was.
But it's within the rejection region. It's in the rejection region.
Yeah, it's definitely in the rejection region. Can somebody help me out and tell me what the p-value is? And this is where it's going to be a little bit evil because it's a two-tailed test. What's alpha? Where's alpha on that picture?
2 negative 1.
Where's alpha? What is alpha? Alpha is 0.05, but where is it on the picture? Good. The little shaded purple spots, right?
Yeah.
So how much area is here then? 0.025. I love it. Now stay with me. Alpha is the area in the tail or tails where my critical z-score is. P-value is the area in the tail or tails of my z-score, my z-star. That's the analogy there, right? Alpha is an area in a tail of the benchmark score. P-value is the area in the tail of my score. So if you just look up negative 2.57 on the z-score chart, you'll almost get the answer. It'll be a really good first step. Because what's the area in the tail of 2.57? You look it up in the z-score chart, right? That's exactly what the hell it was built for. Tell me the area below a z-score. So what do you get when you look up negative 257? 0051?
0051, yep.
I like it. Now the reason that's not quite it is exactly because alpha, this is not alpha, is it? This is half of alpha. So this is not really my p-value. I have to double it to make it fair. Alpha is the total area between the two. So if I have a two-tailed test, I just double that area to make it into a p-value. So what's twice that? So what the p-value, I really desperately want you guys, so that's a little weird. In general, the p-value, you just look up your z-star and you find out how much area there is out there in the tail. That's the p-value, period. If it's a two-tail test, to make it fair, you double it. Because the poor little alpha dude had to get split in half. So I double mine to kind of make it fair to compare it to this dude. Now this is why, this is 0.01. It's only a 1% chance that we're wrong. We got into the rejection region, right? Which means we could do what?
Reject the null.
Reject the null. Support the high. But our claim was the null, so we can reject our claim, right? So, the fact that that p-value is smaller than alpha is exactly the same as my z-star being further in, meaning it's in there. I got a smaller tail, of course, right? This is going to have a bigger tail than mine because my z-score is farther out. So that's another way to test this. Is my p-value smaller than alpha? If so, you reject the null. Support the high. And more specifically, I definitely pass a 0.05. Would I pass a 0.01? If alpha was 0.01, would we have passed? No, we're a little bit bigger than 0.01. We would not have passed. So the p-value, not only, the z-score tells me if I passed or not, the p-value actually goes further and says, well, what level would you pass? Not just I passed at 0.05, it says, dude, you almost passed at 0.01. And a lot of you guys are like, you said a lot of words. So I desperately want you guys. Obviously, if my z-star is further out, its tail is going to be smaller. So if my p-value is smaller than alpha, that actually means my z-score made it far enough. I made it far, so far my tail is smaller. So this number actually tells me what level of test I would pass. It doesn't just say you passed. That's what a z-score does. It actually says that's the level you would pass. That's why in journals they report just the p-value. So people go, whoa, shit, you got 0.00001? Damn. That's stupid amounts of evidence. Instead of just saying, our z-score was sufficient to, they want to actually give, the real probability that I'm wrong. If I can say there's a 0.0001% chance I'm wrong, hell yeah, I'm going to trumpet that. It's going to be at the top of my paper, right? So I'm basically not wrong, sucker. Right? You kind of with me a little bit? All right, maybe. But this feels like chapter 8. It should. It's the exact same thing. The only difference, of course, really, the only real sort of difference was that's a little bigger. But you interpret it the same way. It's almost too simple.
The formula's bigger.
Yeah, the formula's bigger, but the number that comes out, it means the exact same thing as it did before. I use it the exact same way I did before. Okay, maybe. So this is actually, what I'm doing right now is section 9.3. And let me see where they have it. Oh. Yeah, so I love the way they say it. In this book, now real quick, if I would have had to use t-scores, what did we say was weird about that situation earlier?
Population.
This situation, what's weird? What's the first thing you do when you have to go look up a t-score? You have to find its degrees of freedom.
Degrees of freedom.
And what's weird about this one is, which end do you subtract one from? You got two freaking ends, right?
Yeah.
So in general, what you always do is you take the smaller one, because that's going to be more conservative. You with me? So to make a test harder to pass, would I make the scores bigger or smaller to make it harder to pass? Bigger. I want to make it further out. If you want to pass by getting far enough away, then I just move the benchmark further, right? You guys kind of with me? So you're going to kick at the field goal, and you kick it, and I just move the field goal back. I wanted to make it harder for you to pass the test and get on my team. You didn't make it, guy. And it's the guy I like, I just put it with him. So, where am I trying to go with that? Oh, so for this book, there is something else you could do, which is just insane. And this is what I was taught, is you just go more conservative. So for me, I would do degrees of freedom based off of this one.
Small.
Because it's the smaller sample size. That's going to generate a larger t-score. You with me? Because the smaller the sample is, the bigger your t-score has to cover your ass for knowing even less for sure about your standard deviation. So if you have to use t-scores for this kind of problem, you take the smaller sample size to figure out your degrees of freedom. You guys with me a little bit? So back in chapter 8, you just had one sample size. You just had one freaking sample. So degrees of freedom, you just subtract 1 from that one number. Here you just pick the one that's smaller. And then take 1 away from it, and then go look it up on the chart. Not a huge deal. Hopefully. Okay. So a little preview, and then I'll let you guys out of here a little early. The kind of problem for Section 9.3 is exactly what I said. When you have two separate populations, if the women suddenly started scoring a lot better, should that somehow magically affect the men? Do you kind of see what I'm saying? No, right? If for some reason maybe the women make a big study group, and the men are like, study group, you go home, play video games, what the hell? Drink, whatever the hell. So, do you guys understand what I'm saying? They wouldn't necessarily affect each other, so they're independent samples. That's why Section 9.3 has the title it does. Now, what about if I want to test if a weight loss program actually works? So how do you think I'm going to test that?
Use a placebo and use actual weight loss like.
No, let's go even better than that. You do want to have a group of people where their weight, and just see if you don't apply that. But for the people that you're looking at that are in the weight loss program, what do you want to calculate for them to kind of work into this analysis? I want to see if this weight loss program works. If it works, what should happen for the people? The weight should go down. So I want to start with where they are now, put them in the program, see where they end up, and take the difference. Right? I just want to see how different it is. Did you lose weight or did you not lose weight? So those are dependent because I'm talking about the same freaking person, right? So depending on where you start, that definitely affects where you end up. So if I start not very overweight, that's going to affect where I end up. If I start very overweight, I've got a lot more room to lose stuff, right? And obviously it's dependent because it's the same person. Here I had men and women. Nobody's in both groups. I don't care how you try to be. I'm going to put you in one or the other group, right? But for this one, it's the same person. So there's going to be slight differences for the next section in how we calculate the z-score because of the fact that they're not independent samples. They're dependent samples. And we know that when you have that difference, it changes things from independent to dependent. So that's going to be the next section. And then 9.2 is really this whole thing, but with the p-hat stuff. P-hat, q-hat. And its formula gets a little bigger also. Very similarly to how this happened. So we'll go through all that next time. You guys look so happy. Yeah.
So, we deal with standard deviation? We use the p-hat and the q-hat?
No, when you have p and q, they make their own standard deviation. You don't have to be told that. It wouldn't even make sense to give you a standard deviation. Yeah.
What if you have this?
So that's all, guys. You guys can head out.
I do have one question now.
Please give me my calculator back.
What if you, for one population, you have sigma, and for the other one you have s?
Yeah, that's the neat one. Then you still have